Hello, everyone. We're going to continue our journey into solution chemistry by talking about stoichiometry using the molar concentrations of solutions. So let's get started. Okay, we know that molarity relates the moles of the solute to the liters of solution. And I can use this molarity to convert between the amounts of reactants and or products in a chemical reaction because it gives me moles of substances. Remember, the number of moles of a solute is equal to the molarity in moles per liter times the volume in liters. And anytime I can get to moles, I can use stoichiometry even if my reactants are dissolved in a solvent. So let's look at this. Remember, here's my generic chemical equation. My chemical equation has to be balanced before I can do any stoichiometry. But because of this relationship, I can use the molarity times the volume to find moles of A. Then I can use the mole ratio, which comes from the balanced chemical equation, just like I did before, to find the moles of B or C or D, whichever I want to look at. Now I could go to grams of this material, or I could go to either volume or molarity, because I also know that the moles of B is equal to the molarity of B times the volume of B in liters. So solution stoichiometry is slightly different than what we did before in how I get to those mole values of my reactants or my products. I'm using molarity generally to do this, but the general approach is still exactly the same. So here's an example. What volume of H2SO4, now here I have a molarity, is needed to react with 50 mils of 0.100 molar sodium hydroxide? So I know that my molarity is 0.250 moles per liter. The volume is what I'm trying to find. I know that my molarity of sodium hydroxide is 0.100 moles per liter, and I know the volume I use in this reaction is 50 milliliters. This is actually a little bit backwards. What I'm actually doing is starting over here. From the volume of the solution of NaOH and the molarity, I can actually calculate the moles of NaOH. From this 1:2 ratio, which comes from the mole ratio between H2SO4 and sodium hydroxide, I can use that to figure out how many moles of H2SO4 react with the moles that are in this volume of my 0.100 molar sodium hydroxide solution. And then from that, using the molarity, I can actually calculate the volume of H2SO4 that I need to totally react with this amount of my sodium hydroxide. So let's put some numbers to this. Here I have 50 mils, which is my volume of sodium hydroxide. This just converts that to liters, because remember, my volume needs to be in liters in order to get moles. This is my molarity as a conversion factor. So when I do this calculation, I find out this is the number of moles that are in 50 mils of this 0.100 molar solution. So this is the moles of sodium hydroxide. Well, now I start that. I'm going to convert the moles of sodium hydroxide into the moles of H2SO4 using the mole ratios. This is the molar ratio from my balanced chemical equation. This is going to be the molarity used as a conversion factor, but this time it's the molarity, the concentration of H2SO4. And then this is converting from liters to milliliters. Generally, if I start in milliliters, I want my final volume in milliliters. So I do have to do these conversions along the way. But what this tells me, this answer tells me, it takes 10 milliliters of my 0.250 molar solution of H2SO4 to completely react with my given amount of sodium hydroxide. So let's practice. We can use molarities and get volumes, or we can do it the regular way. And once we have moles of our other substance in our chemical reaction, we can use molar mass to get grams. Here's an example of that type of a problem. I'm looking for the mass of PbCl3, right? And I want that mass to be in grams. And what I know is that I'm going to have excess KCl. And my molarity of my lead nitrate is going to be 0.175 moles per liter. My volume is going to be 0.150 liters of my lead 2 nitrate. So based on this knowledge, how can I figure out the amount of lead 2 chloride in grams that will be formed? Basically, I'm looking for the theoretical yield. So let's start. I know I can get the moles of lead nitrate, lead 2 nitrate, if I take the molarity and I multiply it times the volume, which is 0.150 liters. Remember, liters will cancel, and what I get is moles here. And when I do this, I have 0.175 times 0.150, and what I get is 0.02625 moles of lead nitrate, lead 2 nitrate. So all I have to do now is convert the moles of lead 2 nitrate into lead 2 chloride and then use the molar mass to get the grams. So this is just like we did any other stoichiometry problem. So I have 0.02625 moles of lead nitrate. And what I'm going to convert to is moles of lead chloride using the mole ratio. Well, for every 1 mole of lead nitrate, I make 1 mole of lead 2 chloride. So to get the grams that could theoretically be produced, I'm just going to put in the molar mass of lead 2 chloride. That is, let me find my periodic table. I have got lead, which is 207.2. So I have 207.2 plus, and then I have 2 times Cl. So 2 times 35.453. That gives me a molar mass of 278.11. And if I take that and I multiply that by my amount of mole, I get, let me do this again, I get 0.02625 times that 278, and I get 2 3 sig figs, 7.30 grams of lead 2 chloride that is prepared. So again, this is the same type of problem that we're going to do using stoichiometry. It's just that I ended up getting the moles of one of my reactants in a different way because I had a solution amount and not a gram amount. Here's another one. How many milliliters of barium nitrate, and I know the molarity of this barium nitrate is 0.280 moles per liter, is required to precipitate as barium sulfate all of the sulfate ions. So I'm getting a total reaction. And what I know is this total reaction occurs with a molarity of 0.350 moles per liter aluminum sulfate. And the volume that totally reacts is 25.0 milliliters of that. So I want the milliliters of the barium nitrate solution, which happens to be 0.280 molar, that is required to react with all of this aluminum sulfate solution. So I can find moles of Al2SO4 by reacting the molarity times the volume, and I'm going to do this in liters. So I have 0.0250 liters. So those cancel. That gives me 0.00875 or 8.75 times 10 to the minus 3 moles of aluminum sulfate. So now I have moles of my reactant, and I want to figure out the milliliters of the other reactant to affect total reaction. So I'm going to take this 8.75 times 10 to the minus 3 moles of aluminum sulfate, and I'm going to use the molar ratio. This is a 3-to-1 ratio from the balanced chemical equation. So for every 1 mole of Al2SO4 I need 3 moles of barium nitrate. That gives me moles of barium nitrate, but I want milliliters. So I can use the molarity as a conversion factor. For every 1 liter of barium nitrate, I have 0.280 moles of barium nitrate. And the question asks to find the volume in milliliters, so I'm going to do a conversion here. For every 1 liter, I have 1,000 milliliters. So when I look at that, moles of aluminum sulfate cancel with moles of aluminum sulfate, moles of barium nitrate cancel with moles of barium nitrate, liter cancels with liter, I'm left with milliliter. And when I do this reaction, when I do this calculation, I'm going to have 8.75 times 10 to the minus 3 times 3 times 1,000. And then I'm going to divide that all by 0.280. And what I get to 3 significant figures is 93.8 milliliters. So it takes 98.3 milliliters of my 0.280 molar barium nitrate in order to do this reaction. Here's another example, which ups the stakes a little bit more. I want to know how many grams of my copper hydroxide am I going to get? How many will precipitate? The theoretical yield of this. If I react 25 mils, right? So my molarity of sodium hydroxide is 0.350 moles per liter, and my volume is 25.0 milliliters. Then I have another quantity of another reactant. My molarity of my copper sulfate solution is 0.125 moles per liter. And then the volume I have here is 45.0 milliliters. What kind of problem does this look like? I have 2 amounts of the 2 reactants. So this is a limiting reagent problem. So the first thing I'm going to do is figure out the moles of my copper hydroxide that I can get using my sodium hydroxide. For my sodium hydroxide, I have the moles is equal to 0.250 moles per liter times 0.0250 liters, which gives me 0.250 times 0.025. I get 6.25 times 10 to the minus 3 moles of sodium hydroxide. Well, using the mole ratio, for every 2 moles of NaOH, I make 1 mole of copper hydroxide. So if I do this part of the equation, I divide by 2. And this route, if I use all of the sodium hydroxide, will give me 3.13 times 10 to the minus 3 moles of CuOH2. So if all of that sodium hydroxide is consumed, this is the amount in moles of copper hydroxide that I would get. Well, let's look at the volume of, or the amount of product that I get if I used the copper 2 sulfate. So I'm going to do the same thing. I have 0.125 moles per liter of my copper sulfate times 0.0450 liters of my copper 2 sulfate. And if I do this amount, I get 0.125 times 0.0450. I get 5.63 times 10 to the minus third moles of copper 2 sulfate. So let's use stoichiometry to figure out the moles of copper hydroxide. So I know it's a 1-to-1 ratio. So for every 1 mole of copper 2 sulfate, I get 1 mole of copper hydroxide, which gives me 5.63 times 10 to the minus third moles of copper hydroxide. So what's smaller? Is this a smaller number or is this a smaller number? Because I only have enough of sodium hydroxide to make 3.13 times 10 to the minus third moles of copper hydroxide. So this is going to be my limiting reagent. This, not that, is going to be the amount of copper hydroxide that I can make. So let's look at this. If I have 3.13 times 10 to the minus 3 moles of copper hydroxide that I can make, and I know that for every 1 mole of copper hydroxide, I have, what's the molar mass? I have copper, which is 63.546 plus 2 oxygens plus 2 hydrogens. I get 97.5262 grams. And then if I do that math, I get 0.305 grams of copper hydroxide. That's my theoretical yield. That is the amount of the copper 2 hydroxide that will precipitate. So again, I use the molarity and the volume of the sodium hydroxide to find the moles of sodium hydroxide. Then I'm going to use the mole ratio to find the amount of the copper product that I want to make. I have to do the same thing again with the other reagent, because this is a limiting reagent. I have to figure out which one is limiting. I figured out that sodium hydroxide was limiting based on these calculations. When I do that, I'm going to find out the mole amount of the copper hydroxide, the theoretical yield that I could prepare, and then I'm going to go ahead and use the molar mass to figure that out. So this is a lot more work in this problem. These limiting reagents, even in the other mass type stoichiometry problems we did before, were also very steppy. So this is some more steps. Of course, it's a different problem, and this is fair game for any test or quiz in the future. Okay, I will be done with this topic, and then we're going to come back and learn some more about solution chemistry in the next lecture. I'll see you soon.